we've learned that light is nothing more than oscillations in the magnetic field and the electric field. The electric field carries the electric force in red, and the magnetic field carries the magnetic force in blue. If you were watching these waves come at you, if you could actually see what the oscillations look like, you would see the electric field oscillating up and down, the forces are pointing up and down, and the magnetic oscillations would point left and right. The field, the forces are pointing left and right. Now, to produce a wave shape like this, you take an electron and you can wiggle it up and down. These two oscillations in the two fields are always perpendicular, so by convention we don't show the magnetic field oscillations, we just show the electric field oscillations. They're still there, we're just not drawing them. This is polarized light. It's light in which the electric field oscillates in a single direction, up, down, or on one plane. So you can see the vertical plane that the electric field is oscillating in. By contrast, if you consider a lamp or the sun, those electrons are not just oscillating up, down. They're going down and up, but they're also going at this angle and at this angle and horizontally. And as a result, the light that is produced is in all these different directions. So if you were to look at those electric field oscillations head-on, the electric field oscillations are in every direction. You've got some that's up and down, some is at this angle, some is at that angle, some is at this angle. And remember, the magnetic field is oscillating too. We're just not drawing the blue arrow. But for this electric field, the magnetic oscillations would be like this. For this electric field, the magnetic oscillations in blue would be like this. For the horizontal oscillations in the electric field, the magnetic oscillations would be vertical. And for this electric field oscillation, the magnetic oscillations would look like that. This type of light, where the electric field oscillates randomly in all directions, is called unpolarized light. Now, unpolarized light is drawn like this, and remember, these arrows represent the lines of force. So, we can take those force vectors and break them into components. For example, this vector has components that look like that. And this part of the oscillation, those forces on this direction, have components looking something like this. So we've taken care of that angled vector. What about these electric forces? Well, you could draw components for these forces, and they'll look like this. And you can draw components for these forces, and they'll look like that. Because we have the components in the picture, we can remove the resultant, the angled vector. And now look over here at what is going to happen. I'm going to take this vertical arrow and connect it there. I'll take this vertical electric field oscillation and connect it there. And then these vertical components I'll connect to the bottom. And I can connect the horizontal components horizontally on the x-axis. So this will move over, this will move over, and on this other side, these move over as well. So there are two ways to draw unpolarized light. You can draw it like this, or on the right side, you can draw it like this. Both of these represent unpolarized light. In a similar way, we're going to focus on two types of polarized light. It can be polarized horizontally or vertically polarized. Okay, now it's time to see something that sort of relates to your sunglasses, the polarizing filters. Here's the sun, and here is a device called a polarizing filter. It has this line that represents the transmission axis. What does that mean? Well, when you send the unpolarized light from the sun toward the filter, this filter transmits the vertically polarized light, and it absorbs the horizontally polarized light. That's what a polarizing filter is, and they are used in sunglasses. So now I have a question. Let's say you have a scenario like this. How much light makes it out over here? Pause the video and answer that question. Is it half the original amount, a quarter, all of the original amount, none of the original light gets over here? How much is transmitted through the two filters? Okay, we start by remembering, well, the sun emits unpolarized light, and then the vertically polarized makes it through here. So now the light is vertically polarized, and these vertical filters, they absorb any horizontal oscillations. But this doesn't have any horizontal oscillations, so nothing gets absorbed here. All of this light makes it through. So when we compare the amount that's transmitted to the original amount, half makes it through the first filter, and then all of that half makes it through the second filter. So this light is half as bright as the light you had here. Okay, how about this scenario? Now we have two filters. One is vertically aligned and the other is horizontally aligned. And you send light from the sun through. How much light makes it out over here? Take a moment to answer that question. First, you remember the sun emits unpolarized light. The vertical filter absorbs any horizontal oscillations. Any horizontal electric fields or electric forces, those get absorbed. So what passes through is vertically polarized. But this filter, which is oriented horizontally, only transmits horizontally polarized light, and it absorbs vertically polarized light. So none of this passes through, and the answer is you see no light out this other end. No light is transmitted through crossed filters, and crossed means that the axes are perpendicular to each other. This transmission axis and this transmission axis are at right angles. They are crossed.